This is Facility Science Podcast number 9. I am Jason Doolittle, and today I'm talking about electrical safety devices. And specifically, I'm going to talk about 4 different devices, which are circuit breakers, fuses, ground fault circuit interrupters, usually shortened to GFCI, and also called residual current devices. And also the 4th one is arc fault circuit interrupters, usually shortened to AFCI, and also called arc fault detection devices. And if you haven't already listened to podcast number 6, in that one I talk about some basic concepts of electricity and power. I basically describe voltage, current, and power. You might want to listen to that one first, because I'll be talking about voltage and current in this one, and you'll get some background if you listen to number 6 first. So I'll start with 2 types of devices, the circuit breaker and fuse, which have a similar function, and that's to protect against overcurrent. And so we'll start with a circuit breaker. So a circuit breaker opens a circuit when more than the rated current is detected. And in the context of power distribution inside buildings, a circuit breaker is most often a switch that can be manually operated to turn power to a circuit on and off, and will also disconnect the power automatically when excessive current passes through it. And some of them can even be electrically operated by some remote control mechanism. That's usually the larger circuit breakers that are remotely controllable. And so the primary function of the circuit breaker is to automatically disconnect the circuit when too much current is flowing through it. And then the secondary function is that you can use that switch as a power disconnection mechanism for servicing of the electrical equipment. Many circuit breakers, maybe practically all of them, have an indicator to notify the operator that the breaker tripped off due to a fault condition rather than was turned off manually. And in some cases, the trip condition is indicated by a third switch position. So there's an on position and an off position, and then also the third position, usually in the middle, a tripped position, so that you can tell immediately when you look at the breaker that this one is on, this one is off, and that one is neither on or off, it's tripped. And usually you have to move the breaker, the switch, from the trip position to the off position before returning it to the on position. In other cases, again, this is usually the case in larger circuit breakers, the trip indicator is a second mechanism that provides some visual indication of a trip and then provides some way to clear the trip and reset the breaker. Now, a circuit breaker is meant to protect against 2 different but ultimately related fault conditions, and that's the overload condition and the short circuit. So an overload is a condition where too many devices or devices that draw too much current are attached to a circuit, and those devices in combination draw more current than the circuit and the breaker are rated for. And when that high current is detected by the circuit breaker will trip and disconnect power. And this is important because high current causes heating in the wire. Hot wires can melt the insulation. Maybe even if they're hot enough, they can melt themselves. But normally the problem is that you melt the insulation, and then the hot wire comes in contact with something flammable, and you start a fire, and that's a bad situation. And so that's why it's important to protect against overload. And the circuit breaker is sized based on the size of the wire that is going to be carrying the current, and also the device that will be operating on that circuit. The other condition, a short circuit condition, is when a circuit is completed by an unintended path. And in practice, this means that a connection has been made directly from the line conductor, the hot wire basically, to either the neutral or the ground conductor. This can happen because of a wire coming loose inside of an appliance, or a screw being driven into a conduit, or someone's sticking a fork into the electrical outlet or whatever. And since these conductors, the wires that are carrying the electricity, are designed to carry current to the load, the appliance or the light fixture or whatever, without consuming much energy themselves, a direct connection between the line conductor and one of the other conductors, the neutral or the ground, will have a very low resistance, which means there'll be a very high current. And I stated before that a very high current is dangerous because it heats up the wires to the point that they can start a fire potentially. And devices and raceways are often designed, so appliances basically, are often designed and installed so that if a live wire comes loose inside, it will contact something that is effectively guaranteed to create a short circuit. For example, if you have an appliance with a metal case, like a closed washing machine or something like that, the metal case will be bonded to the ground conductor, and the ground conductor doesn't carry current in a normally operating circuit and is they're essentially as a safety to carry fault current and create a deliberate overload condition rather than creating a dangerous situation. And we want this to happen so that if an exposed conducting part becomes energized, right, so the metal case of our washing machine, for example, the power will be immediately disconnected rather than create a shock hazard for anyone that might touch the appliance. So basically, I said that an overload and a short circuit are related, and what I meant is in the sense that a short circuit will, by design of the system, hopefully create a deliberate overload, which will then trip the breaker. And there are two mechanisms that are used to detect high current by a circuit breaker and break the circuit. These two mechanisms are temperature and magnetism. So the first one, temperature, talked about before, that electrons flowing through a wire or anything really will cause that wire to heat up. So some breakers will use something like a bimetal strip, which is a device that is basically two different types of metal sandwiched or stacked together and attached to each other. And these two different types of metal have different expansion rates as they heat. So you heat them up and they expand at different rates. And what the result of that is, when you heat this device up, it'll bend. Or when you change its temperature, and anyway, it'll bend, it'll straighten up or bend or whatever. So we can put a device like this in the path of the current. When the current gets high enough that this bimetal device bends enough, it will disconnect the circuit. So that's one method that a circuit breaker will use. And the other method is magnetism. So there's a device called a solenoid, and when current flows through a wire, it creates a magnetic field around that wire. And so if you make a coil of wire, wrap it around and around in a coil, the current flowing around and around that coil will create a magnetic field that sort of stacks on itself as many times as you've wrapped the coil. So the strength of the magnetic field will be basically proportional to the number of turns on your coil. And so if you've ever, maybe when you were a kid or something, you wrapped some wire around a nail and connected the wires to a battery, and then your nail became a magnet. So there's a device called a solenoid, and it's used very commonly in anytime we want to basically convert electrical energy into some type of mechanical impulse. And what a solenoid is, basically, you take a coil and you put a steel plunger inside of it so that when you energize the coil, the plunger moves. And then when you de-energize the coil, usually they're spring-loaded, so the plunger goes back the other way. And so the way a circuit breaker uses a solenoid is the solenoid plunger will be attached or somehow pushing on some part of the circuit breaker. It'll be trying to push the circuit breaker into the off position. It might be pushing on something or pulling against a spring or something like that. It depends on the exact design of the circuit breaker. But basically the idea is the higher the current goes in that coil, the stronger the magnetic field will be. And the circuit breakers are designed so that when the current gets to a certain level, the level that the circuit breaker is rated to trip at, the strength of the magnetic field will be enough for the solenoid plunger to operate whatever mechanism it's supposed to operate to disconnect the circuit. So those are the two mechanisms we use, and many circuit breakers use both of those mechanisms, and some use only one or the other depending on the exact function. And the large majority of circuit breakers are in our power distribution equipment, distribution panels, and switchboards, breaker panels. However, there are also circuit breakers in all kinds of control panels and appliances and other things. And in general, when you're dealing with a circuit breaker, it's a good idea to identify the problem that caused the breaker to trip before turning the power back on. All right, now we'll talk about fuses. And fuses are similar to circuit breakers in their function. They protect against overcurrent conditions and short circuits. And a fuse, though distinct from a circuit breaker, is basically a piece of wire. It's just a piece of wire. But it's a piece of wire that's specifically designed, sized, and shaped to carry electric current as part of a circuit under normal conditions, but then to melt and break, effectively opening the circuit, cutting off the flow of current when too much current flows. And fuses come in all shapes and sizes, from very tiny that fit on the tip of your finger to massive fuses that are used in power distribution. And there's some things to know about fuses and circuit breakers that we can talk about just together because they accomplish the same function. And so you always want to use a fuse or circuit breaker that is designed for the particular application. So for example, the device should break the current under a fault condition, but not break the current under a condition that isn't a fault. And you might think that this should be really a simple idea. If the current goes over the rated value, open the circuit. But it isn't necessarily this simple in practice. So some devices, like motors, for example, pull a very high amount of current, often much higher than the rated amount, for a very short time when they start up. And also, they happen to have a property, because of the way they're constructed, that they can tolerate an excessive amount of current for a short time without being too damaged. And so for this type of device, you want an overcurrent device, so a breaker or a fuse, that will tolerate a certain amount of excess current for a short time before opening the circuit. So it won't trip immediately if the current goes over the rated amount. And the definition of a short time and immediately depend on the actual load in question. But then there's other types of devices like electronics, which are very sensitive to excess current because their very small parts are easily damaged by, for example, heat. And so for these devices, we want to open the circuit as quickly as possible once the current limit has been reached. So in the case of, say, a circuit breaker designed to supply power to a motor, we want to make sure that say bimetal device, that the temperature switch inside that circuit breaker is designed so that it'll tolerate current a little over the limit for a short amount of time, and then if it lasts too long, it will open the circuit. And in fact, some motor control devices only use the heat or the temperature switch. And then obviously we still want to have protection on there for if, for example, we short circuit the motor, that if the current goes way high, we'll have a solenoid device to pull it off. And the same thing with fuses. A fuse that controls a motor, they're designed to either heat up slowly or to break slowly so that they can handle some amount of current over the limit for a short duration. Now, for the electronic devices, we want only the fast acting fuse. We don't want the slow acting, say the bimetal strip device to protect the electronic device. So we want a fuse usually that will open very quickly on even the slightest overcurrent condition. So the point being, it's not necessarily simple to decide what type of overcurrent device, and we should use the one that's designed for the application. And another thing is that the device should be rated, so the circuit breaker or the fuse should be rated to handle the voltage it's going to be operating in and also the available current. And this has to do with arcing. So anytime you open an electric circuit in which current is flowing, an arc will form at the point of the disconnect. And disconnecting devices, including circuit breakers and fuses, have to have some means to contain and extinguish any potential arc that could form. They have to be able to handle this situation if they're going to be reliable to break the circuit. And the distance over which an arc will form mostly has to do with the voltage present, and the ability of an arc to sustain itself and potentially expand and cause all kinds of damage, say over a longer distance than what was originally required to start the arc, has mostly to do with the available current. So basically the power supply and the upstream overcurrent protection devices. And so arcing, for a little more detail in this context, is when electric current travels through the air, which creates a very high amount of heat. And we generally think of air as an insulator, as in it doesn't conduct electricity. But for any given voltage, there is a distance through air over which current will flow. And the higher voltage, the longer the distance that can be jumped through air by the current. And the most spectacular example of arcing is lightning. So a lightning arc, that's a bolt of lightning, can be several miles long. And that long of an arc through air requires millions of volts of potential difference, so voltage between the points of the lightning, the beginning and the end, and say the cloud to the ground. But for the voltages commonly found inside our buildings, 240 volts or 120 volts, the arcing distance is very small, so some fraction of a millimeter, tiny distance. You might notice that sometimes when you plug something into a wall receptacle, you see a little spark. That spark is another example of arcing. It's the current jumping across the air gap right before you actually make contact. And I'll use a fuse as an illustration. So when the wire in a fuse melts, it creates a gap where there's no conducting material. The wire breaks, melts apart. But the size of the gap has to be big enough to prevent a sustained arc from forming. And this generally means that a fuse for a higher voltage has to create a bigger gap than a fuse for a lower voltage. And so what that also means is that it's not safe to use a fuse rated for a smaller voltage than the circuit you might want to put it in, because that fuse, even though it has the right current rating on it, if it doesn't have the right voltage rating on it, a high enough voltage rating, a break in the fuse from an overcurrent condition might not actually be able to break the circuit, because you might just get arcing across and current will just continue to flow across the air gap. And then the fuse also has to have a means of extinguishing whatever arc does form. And in some fuses, this can be accomplished by just creating a large enough gap fast enough that the arc won't have time to become established. And some fuses for higher power situations are filled with other materials, such as various kind of gases or even sand, to control the arcing. And then circuit breakers, similar situation. You want to use one that's designed for the voltage that'll be present in the circuit, and also that's able to handle the available current upstream so that an arc can't form and just bridge the air gap and burn everything up. So circuit breakers, they use similar mechanisms to prevent arcing and to extinguish arcs. The bottom line, the take home from this particular section, is that it's important to use the circuit breaker or the fuse that's specified by the equipment manufacturer or the electrical engineer. And if you're in a situation where you have to make a choice to use one that wasn't the one that was spec'd or recommended, make sure that the person who's deciding which one to use understands these issues and knows how to choose a circuit breaker or a fuse. All right, there's also things called resettable fuses, some of which are even self-resetting, which kind of contradicts what I was talking about before, because the fuse I was talking about before is a piece of wire that melts, and once it melts, it's done. You have to take it out and throw it away and put a new one in. And these resettable fuses are typically found inside electronic devices, and they protect the device from damage due to overload or short circuit, just like the fuses and circuit breakers we've been talking about. And typically, with these types of devices, clearing the fault condition and allowing the device to cool will reset the self-resetting fuse. These are typically very simple devices and are more like the circuit breakers I was describing before than they are the fuses. And I don't really know for sure, but I imagine these things are called fuses instead of circuit breakers because they're used inside electronic devices where we would historically have used fuses, and the people who developed them for that purpose didn't think it was necessary to use a different name for a device that accomplishes the same purpose at the same part in the circuit, just works a little differently. And the choice between circuit breakers and fuses depends partially on how often we expect the trip condition or the overcurrent condition to occur. If it's something that's going to happen, if it's something that we expect to happen kind of regularly, we want to maybe use a circuit breaker instead of a fuse. Although circuit breakers are more expensive to install, but then you don't have to replace them often like you do a fuse. You have to replace every time it blows. Also, who we expect to be handling the situation. So if we're expecting an untrained user of the device, we would want to use more likely a circuit breaker. And if we're expecting someone who understands the dangers of operating in a circuit around live parts or parts that potentially might be live, then using a fuse is okay. So again, the decision just depends on the exact details of the situation, whether we're going to use a circuit breaker or a fuse. All right, now the next device I want to talk about is a GFCI, or ground fault circuit interrupter. Again, like I said before, this is often called a residual current device. I think mostly in North America or maybe just the US, we call them GFCI, ground fault circuit interrupter. And in Europe, they call them residual current device. And other places maybe vary. So again, we call these GFCI, or sometimes even shortened to GFI in the US. So that will be my default terminology. In your home, you probably have an electrical outlet in your bathroom or kitchen with two buttons on it. And they say something like test and reset. And maybe you have a portable appliance like a hairdryer or a fan or something, and that device has a big plug on it, bigger than normal, with two similar buttons on it. So that device with the two buttons, either the receptacle on the wall or the thing on the end of your appliance, or even sometimes a breaker in your panel is the GFI, the ground fault circuit interrupter. And so what is this thing for? So when you touch a live wire in the typical configuration found in your home, current will flow through your body, which isn't something you really want. And your body isn't a very good conductor of electricity, so it won't be a lot of current. And most likely, it won't be nearly enough current to bother the 15 or 20 amp circuit breaker protecting the circuit. Unfortunately, it only takes a very small amount of current, 100 milliamps or less, something in that neighborhood, to stop a person's heart, which obviously the person won't survive if they don't get immediate help. So the GFI helps protect against this type of danger. So how does it do this? Well, in a normally operating circuit in your house, the device is connected to two wires at the wall receptacle, the hot wire and the neutral wire. And if everything is operating properly, any current going into the device from the hot wire should leave the device on the neutral wire. So if the current on those two wires are different, that means that current is flowing from the device to somewhere else, which in a properly functioning circuit should never happen. So the GFI device monitors the hot and the wire and the neutral wire, and then disconnects the circuit very quickly, so on the order of 25 to 40 milliseconds, if even a small difference is detected between the current on the hot and the neutral. And the small difference is typically in the range of 5 to 30 milliamps. So milliamps, that's a thousandth of an amp. So 5 to 30 thousandths of an amp. And so we call this condition of current flowing outside the intended circuit a ground fault. So the GFCI is a ground fault circuit interrupter. And these devices are designed to open the circuit for a very low ground fault current, typically lower than would be harmful to you, and also faster than a ground fault current would hurt you if the ground fault current is high enough to hurt you. In addition to protecting against electrocution, which is really its primary function, the GFCI can also help protect against fires and equipment damage in ways that a normal circuit breaker can't, because a normal circuit breaker only protects against too much current. It doesn't protect against current flowing somewhere where it shouldn't be flowing, which again can electrocute you, but can also in certain conditions cause fires or equipment damage. And these are required mostly in residential places, required by regulation or law, mostly in residential places and in places where there's a higher chance for an accidental ground path to occur. And mostly that means places where people may be working near electrical devices and also might have a higher than normal chance to get wet or be interacting with water. That's like bathrooms and kitchens and swimming pools and garages and patios and stuff like that. All right, now the next device is the arc fault circuit interrupter, AFCI, also called arc fault detection device. And the AFCI detects a type of fault not detected by either a circuit breaker or a ground fault interrupter. And that type of fault is called an arcing fault, probably not surprising. Now, arc faults typically happen between conductors in a raceway or a cable where the insulation has been damaged. And this is one of the reasons that many safety regulations forbid the use of extension cords in certain situations, and why your fire inspector might tell you to remove an extension cord that's running across the floor or under a door or a rug or something like that. Because the impact or abrasion of the cord can cause the insulation between the wires to wear or break, allowing the conductors to come close enough together to create arcing between them. Also, it can cause maybe just one of the wires to break inside its insulation, which can cause then arcing between the two pieces. And this is usually an intermittent condition, and it typically gets worse over time as things start to burn and melt. And sometimes the result is just a failure of the cable or device. Eventually you get enough arcing that you get oxidation on the conductors and you melt something apart, and you get instead of getting an arc fault, you get an open circuit. That's what happens sometimes, but other times the very hot arc comes into contact with something flammable and starts to fire, and that's the situation you don't want. And arcing faults can also happen inside of worn or abused or poorly made appliances, and also it's common they can happen where cables are spliced together in junction boxes or at switch boxes or receptacles. And so we classify three basic types of arc faults: serial arc faults, parallel arc faults, and ground arc faults. So a serial arc fault is when arcing occurs between two parts of the same conductor. So the example I gave before, if you walk on the extension cord too much, when it's underneath the carpet, and you end up breaking the conductor inside its insulator, and then the two ends of that conductor start to sort of spark against each other. That would be a serial arc fault. Another common example of a serial arc fault is when you make a splice inside of a junction box or something, where you put some kind of connector, a wire nut or something like that onto to attach two wires together, but the connection wasn't made properly, so the two wires can separate slightly inside the splice. You get an arcing fault in the splice. And then a parallel arcing fault occurs between two different wires, so that's the hot and the neutral, or between two phases of a multi-phase circuit. So it can happen in all those same situations where you just have these two wires that are supposed to be separated from each other somehow come close enough to each other to maybe touch sporadically a little bit, or close enough to create an arc between them, but maybe not in direct contact enough to create a short circuit and open the circuit breaker. That's a parallel arcing fault. And again, you can get the same kind of heat between those two wires where you can get hot enough to set things on fire. And then a ground arc fault occurs between the hot wire or the neutral wire and ground. And a GFCI will typically handle the ground arc fault, but not the other two. Now, arcing is normal in many situations and electrical devices. So an AFCI device, an arc fault interrupter, attempts to open the circuit only on abnormal or potentially dangerous arcing. So they want to make sure they open it on the dangerous situation, but not open it on a normal arcing situation. Like I said, many appliances and many electrical devices, and in many situations, arcs happen kind of as a matter of course. I mentioned one earlier when I was talking about what arcing is. Sometimes when you plug a device into the receptacle, you'll get a little arc before you make full contact. So you don't want to trip the arc fault interrupter on those types of normal arcing situations. And so these devices attempt to make a distinction between bad arcs and okay arcs by analyzing the alternating current waveform and looking for the characteristics of arc faults. And this is not necessarily straightforward or easy to do. And so AFCI proponents point to the potential and actual life-saving benefits of detecting and correcting arc faults before someone gets hurt. This is an important thing to do. But many other people, including many electricians, complain that these devices are too sensitive and that nuisance trips are too common to make the devices worth relying on for actual life safety. Because people either end up replacing them with non-arc fault interrupter devices, or they just learn to ignore them and reset them without looking for a problem. I can't really tell who's right. So while you should probably install them where required by laws or regulations in your area, otherwise you'll just have to make up your own mind on their utility. And because of the statistics about how many people are killed or hurt in fires that are caused by electrical faults, many of which are arcing faults, AFCI devices are required in many places, mostly in the US, I think, and especially in certain residential areas where people are more likely to be harmed by an electrical fire. So this is, places where people sleep, or maybe places where there might be children around. And that, I think, is all I have to say on this topic for now. If you have any questions or comments about this, or suggestions for other topics, maybe something that I missed or got wrong, you can let me know via email at podcast@facilityscience.com. I hope this was helpful to you, so thanks for listening.